Good evening, everyone. I am Rashi from Amity Center for Nanomedicine, Amity University, Uttar Pradesh, and the title of my presentation is Unlocking Janus Particles, the Power of Post-Synthesis MOF Modification. So basically, I'll tell you about what MOF is, what are the applications of MOF, what are Janus particles, how we have fabricated a Janus particle out of an MOF in this presentation. So what are MOFs? Basically, they are your Lego sets or Tinker toy sets for chemists, where metal ion act as a building block and organic clinkers connect them, forming a 3D porous network. And the size and the pores of this material can be precisely controlled via synthesis process, this makes them a very tailorable material, and this the whole chemistry of fabricating an MOF can be a part of a reticular chemistry. So what are the applications of MOF? They can range from catalysis to sensing to drug delivery and gas storage and separation. So in catalysis, they can be functionalized apparently to act as a catalyst to degrade or to absorb some materials. They can act as a as a bed, and they can also be immobilized with various antibodies, enzymes, and other things. And for gas storage and separation, they have a porous structure, so they can store gas in those pores, and via reticular chemistry you can make them as molecular sieves, and allowing specific gases to pass and specific gases to not pass. Then what are Janus particles? Basically, your Janus particles are named after Roman god Janus. They're particles having two sides or two hemispheres in one single material, and each side possesses different chemical or physical property. So you can functionalize the material according to your own requirement or whatever your application is. And this asymmetry open many doors for various applications, including targeted drug delivery or a self-assembly, microfluidics, catalysis, etc. So basically, one side can act as a diffusion area, and other side act as a catalyst. For example, if you take as a catalyst, so why I chose MOF for to make it into a Janus particles? As you know, they have inherent porosity and diverse functionalities, and this modification allows for spatial control of properties, which create unique materials with tailored and better performances. So you can say कि it unlocks a new level of material. You already have an MOF which has humongous properties. When you allow it to become a Janus particles via methods that I'll discuss in previous incoming slides, you unlock a next level of material which can be used for various purposes. So, what is PSM and what are the strategies for post-synthetic modification of MOF? So, basically, I use PSM or post-synthesis modification as a tool to convert my MOF into a mobile Janus particle. So, it's a technique that allows further modification after their initial synthesis to control over functionalities without compromising the basic structure. And there are three types of PSM that we mainly use for this modification. One is linker replacement. So what happens in linker replacement is you either via steric hindrance or via linker functionality or linker stability, by taking these three into, you can replace linkers. So specific regions of the MOF can be targeted for precise modification. Next is your linker addition. Functional groups are attached to the existing linkers on one side of the MOF. This can be achieved via click chemistry or by a bioconjugation or by surface grafting. So, and the third is your guest molecule encapsulation, in where we introduce guest molecules into the pores of MOF. It can be done via diffusion or via solvent-assisted linker exchange. So the benefits of linker replacement is it introduces an entirely new functionalities which was not present in the original linker, and you can have a Janus MOF which have two distinct properties on each sides.
Yeah, Rashi, just
Yes, sir.
you need to open your cam. Yeah.
Hello.
You
Yes,
need
sir.
to open your web camera. You need to open your web camera.
So wait, I'll I tried earlier, but it was not. Wait, I'll try. So
Your,
is it open now?
I think your, okay, now
Yes, yes,
open.
yes, it's
Yes,
open.
okay.
Uh,
But slide, you said, okay, now, yeah.
uh,
Okay, please go ahead.
okay, okay, okay. So as I was saying earlier, linker replacement, it basically targets specific regions of the MOS for precise modification. Then linker addition attaches functional group after the synthesis of MOF within the existing framework, and guest molecular encapsulation means the introduction of new molecules into the pores via diffusion or solvent-assisted linker exchanges. So by and what are the application of the MOF-based nanoparticles? This is targeted drug delivery. One on the one side, you can load your drugs, and other can be used for targeting. Another is catalysis. As I said earlier, one can be used as a catalyst, and other can be used as a reactant to control the product diffusion. And the third and the most important is sensing. Basically, one side can you analyze the target, and the other side can generate a electrical or any kind of signal that you want to incorporate into your sensing mechanism. So by taking all the information and all the knowledge that I had, that introduced you to, I made an zirconium-based MOF, bidentate zirconium-based MOF with iron as an engine via PSM technology, and this comes under your linker edition. And in this, we have first made a bidentate MOF, zirconium-based MOF, where we have zirconium as a metal center with two kind of linkers present in the MOF. So one is pyridine-based and other is carboxylic-based. So the carboxylic group will further help in the your addition of towards the zirconium based MOF, and as the zirconium based MOF is formed, when we'll add the Fe into the structure, the pyridine based linkers or the pyridine sites will take your iron, so it will have two kind of metal moieties. So what we fabricated and characterized this FEZR MOFJP via PSM technique. Then the speed optimization, as you know, one side is reactive towards a fuel, which is hydrogen peroxide in our case, and the other side, the zirconium-based MOF, will act as a catalyst towards the degradation of amoxicillin antibiotic, which you have taken as a model antibiotic. So this whole work was to form a Janus particle, self-moving MOF-based particle, which can degrade your antibiotics present in effluent water. As we all know, AMR is at rise, and it is predicted that by 2050, 50 million deaths may take place. So, by curbing this problem at the base level, we are not allowing the antibiotics in the effluent water to go back into the biological systems, and we can prevent this AMR. So the optimum speed that we obtained was 190 micrometers per second at optimum concentration of an MSA and fuel concentration. So basically, we have added an emotion stimulating agent. What it does is, when it reacts with fuel, it creates bubbles which will push the MOF in forward direction. So sometimes due to over fuel concentration or lower fuel concentration, the bubble generation is not stabilized. So MSA will reduce the friction and stabilize the bubble formation, and the formation of this FEZR MOFJP is confirmed by the FTIR and XRD as well. And if EDAX also confirmed the presence of iron in the zirconium bidentate MOF as well as XPS. So
Okay,
there is
please consolidate your work. Yeah, now
ah,
time is up.
okay, sir. So the optimum degradation that we obtained was approximately 60% at optimized MSA and fuel concentration. And as you can see in the HPLC results, the dark blue sharp line is for the undegraded concentration, that is our first 100 ppm of amoxicillin, and the light green line is for the degraded amoxicillin. So as you can see, almost the beta lactam group of the antibiotic is broken, and that's why we don't see any strong peaks for amoxicillin. And as you can see, this is the Janus motor that I've prepared, which is moving in water, and as it's moving, it's also degrading your antibiotics. So
Okay, please give me the conclusion.
the conclusion is what we have employed MOF as a base material and further modify it to make a Janus particles, and this duality allows the assembly allows for the assembly into complex structures and open doors for diverse application, which is in our case catalysis. And we have optimized the speed as 190 micrometers per second with degradation as 59.76 percent in less than 1 hour. Thank you.
Okay, thank you very much for your.
Good evening to all. Myself Neha. I am Junior Research Fellow under the supervision of Dr. Mohammad Zubair Ansari, NIT Srinagar. The title of presentation is Growth of Single Phase CZTS Nanoparticle by Hydrothermal Method. These are the outlines. Introduction. The CZTS copper zinc tin sulfide is a quaternary chalcogenide compound semiconductor. It is a tetragonal structure system which has lattice constant A equals to B equals to 0.54 nanometer and C equals to 1.09 nanometer. It is non-toxic. It has non-toxic and earth abundant element. It is a P-type semiconductor material. Why we use CZTS? CZTS because it has a high optical absorption coefficient, approximately 10 to the power 4 meter inverse, and it has a direct band gap approximately 1.5 electron volt. Also, it has a high photoelectric conversion efficiency. These are the methods to synthesize CZTS. First is microwave, second is solid state reaction, sol-gel, solothermal, hydrothermal. We try to synthesize CZTS by hydrothermal method. First of all the precursors dissolve in DI water and stearin. After that, the solution was transferred into the autoclave and heated it at a different temperature. Then centrifugate the sample and drying. Then we get the CZTS in the powder form. These are the XRD pattern of different sample at different temperature. In the first plot, CZTS is synthesized at temperature 140 degrees Celsius. The XRD peak of CZTS occurs at different 2 theta values corresponding to the lattice plane 112, 200, 220, or 312. But some low intensity peak of SN2 also occurs. When we increase little bit temperature, it is 160 degrees Celsius, then one peak of SN2 will be resolved. Again, when we increase the temperature, then we synthesize pure single phase CZTS. In this table, these are the standard 2 theta values of CZTS. These are the planes, and it is observed value of 2 theta, which is nearly equal to the standard value of 2 theta. Here, the crystalline size of CZTS nanoparticle is 37.25 nm, which is calculated by stereo formula. It is UV visible absorbance and band gap plots. The CZTS nanoparticle shows broad absorption spectrum in the visible region, which prove that it is suitable for many photovoltaic application. And here the band gap obtained was 1.7 electron volt. Thank you so much.
Sir, myself, Manjunath B.
Yeah, I can hear your voice. So mention all the mention.
First of all, the basic word. Sir, hear my voice, sir? Audible?
Yeah, yes.
The word polymer is derived from Greek word poly means many and meros means part, are units of higher molecule mass. A polymer is a single straight line. You can say that a polymer is a macromolecule composed of many repeated subunits in a regular manner. So, first of all, why are you choosing this topic? Means very interesting area. Nowadays, has fully depend upon that polymeric material. That's why firstly concentration of this topic. Then I will choose this topic and then focus on that topic. So this is the regarding to information about that polymer, and then what is the importance of polymer, application of polymer, types of polymer, and classification, examples, so on. So straight away I will say that little bit, just highlight of that few points in this today international conference settings. A polymer is a chemical compromised of repeating monomers with the same chemical structure. And the next point is the conductance is the ability of a material to carry electrical charge. So once you are the electrical charges, if you want, then automatically you can do that the conductance to applying. So automatically ability to material carry electrical charge. So then the fourth point is conducting polymers are organic polymers that conduct electricity. Such compounds may have metallic conductivity or can be semiconductors. So straight away, this slide is including so many type. First of all, polymer and conducting polymer, and conducting polymer, polymers structures, and how to charge carry in this materials. So these are the main importance of agenda. This slides consists. Next, right away go to the polyaniline. So polyaniline has attracted considerable attention not only from fundamental scientific interest but also from practical applications due to its novel properties. What are the novel properties? Means special doping mechanism, good environmental stability, low cost, and high conductivity. So these are the novel properties, choosing easy to available synthesis for our chemical synthesis. That's why you
Yeah,
are choosing
Manjula.
this
Yeah,
topics.
Manjula, when you please you turn on your camera. Yeah.
Okay, okay, sir.
Okay.
Now, sir.
Yeah.
Okay. So this is the structure of polyaniline. So like this. This is the structure of polyaniline. So first structure is a monomer aniline. Say have like this. Okay. Polyaniline has a greater unique structure containing an alternate arrangement of benzene rings and nitrogen atoms. Once again, polyaniline has a greater unique structure containing an alternate arrangement of benzene rings and nitrogen atoms. Next, how to synthesis of polyaniline. So using this flowchart, you can synthesis the polyaniline. So first of all, you take aniline and then hydrochloric acid HCl, and then combining with after stir after 30 minutes of stir, then this chemical that phenomena is called as aniline hydrochloride. Then after next, again that with the help of stirring and then plus adding APS ammonium persulfate, again stirring with the cold temperature with help of ice -4 degree temperature, and then black, separating that you can finally you get black precipitate. After you get this black precipitate, then you can after dried at 60-degree temperature in hot air vacuum. So that last finally you can obtain that our samples. That sample is called as a polyaniline. This is the pure polyaniline. So next, after this castrations, you take sorry. See next slide. After you obtaining the equations XRD, SEM, AC, DC, and LPG properties. First, you take the aniline like this. Graph comes like this. It means a broad peak. So second, this peak means this is the straight lines. This peak is means this pattern is straight patterns, and obtained find out the according to the find out Skerrer method, D-base Skerrer formula, we can find out the crystalline grain size, and then H is to K is to H Miller index HTL value, and planes, crystal planes. Okay. So first one is a broad peak. You obtain the broad peaks. That's why it's easy to straight out. This is the amorphous nature, and then this is the crystalline nature. Only these two parameters bifurcation, and then third parameter is how to find out the crystalline grain size, and the 4.1 is the crystal planes. Using it to the help of formula of DHKL is A square plus B square K square plus L square. With the help of this phenomena, you can find out, and then with the help of origin graphs, you can draw the like this. And then the XRD instrument shows the structural properties. No one said that automatically, and then just only fluoride. When consider the pure Pani, and figure shows that XRD pattern has a broad peaks, it means that pure Pani is amorphous nature, and then pure Pani peaks the range 25 degree. See like this 25 degree. And the promise, the XRD results are consistent with the result obtained by the other research groups. The average crystalline size of the Pani are estimated to be approximately 2.86 nanometer, are calculated by using the D-base Skerrer formula. The formula D is equal to K lambda divided by beta into cos theta, where D is the crystalline size, lambda is the wavelength, K is the crystalline shape factor, and good approximations of 0.9 beta if FWHM full width of maximum and 2 theta is angle degree.
Yeah,
So
then
next
can you
characteristic.
go to conclusion?
Sir?
Please proceed to conclusion. Your time is almost 8 minutes. Yes, gone.
Oh, okay, sir. Okay,
Yeah,
sir. I will
please.
give 2 minutes.
No.
2 minutes within I will complete, sir. Okay. The next characterization is SEM, scanning electron microscope. So straight away scanning electroscope means surface. You can study the surface morphology structures. So figure shows that SEM is nano-composite. In their graph shows the particle is agglomerated, highly and non-porous, granular size, strong interaction chain, others. And upon very high magnification, its observation reveals that presence of homogeneously distributed PnNiO within the polymer samples. The same study conducted on these samples shows numerous agglomerated particles on the pores. And next characterization is DC conductivity.
Okay, almost is finished. Okay. Yeah.
I thought.
Yeah. Now,
Next.
yeah.
Yes. Okay, sir. Okay, thank you.
Yeah, thank you. Thank you for your presentation, Vaishali.
Good evening. My name is Nida Khan, and I'm doing research under Professor Zeba and Siddiqui, Department of Chemistry, Aligarh Muslim University. My research, I'm going to present my research paper entitled Selective Esterification of Glycerol over Ionic Liquid Functionalized Cellulose under Energy Efficient Microwave Irradiation. Now coming to introduction part. Esterification of glycerol with acetic acid produces monoacetin, diacetin, and triacetin. Among them triacetin is widely used as fuel additive and also in cosmetic industry. Therefore, we develop a green and sustainable route for synthesis for selective esterification of glycerol. Now coming to synthesis part of catalyst, that is IMD-Si HSO4 at cellulose. First ionic liquid was synthesized. We take equimolar amount of imidazole and triethoxypropyl chlorosilane under nitrogen atmosphere at 110 degrees Celsius temperature. Then this formed product ionic liquid was undergo an ionic exchange in presence of sulfuric acid. And then this ionic liquid supported on cellulose at room temperature. Then our product is formed. That is our heterogeneous catalyst IMD-Si HSO4 at cellulose. This is procedure for acetylation of glycerol in presence of catalyst. We synthesize triacetin by taking glycerol 0.1 mole and acetic acid 0.6 mole in presence of catalyst 20 milligram under microwave irradiation at 100 degrees Celsius. The The progress of reaction was monitored by thin layer chromatography, and the confirmation of triacetin formation was done by GCMS and FTIR spectroscopy. Here we can say we can see the peak at 218 is of triacetin, and in FTI spectra, the peak at 2854 is of CH stretching of triacetin, and the peak at 1740 was corresponding to triacetin. We optimize our catalyst. We optimize this reaction by using different catalysts. We synthesize different catalysts to optimize the reaction. First, we tried different ionic liquids by changing chloride ion by metallic ion. Then we see that there is increase in triacetin yield. Then we tried acidic ions. Here we see that IMD-Si HSO4 is best among all acidic ions.
Yeah, can you open your video also? Yeah.
So my video is open.
Oh, I couldn't see. Okay. Okay.
Okay.
Now please go ahead. Yeah.
Okay. Then the surface area plays an important role for rate of reaction. So we supported our ionic liquid to different support material, and we see that the best ionic liquid, the best catalyst was IMD-Si HSO4 at cellulose as 100% conversion of glycerol, and we got triacetin 99% selectively and under 8 minutes, which is minimum time. Now coming to result and discussion part. IMD-Si HSO4 has been characterized by various techniques like FTIR, SAM, EDX mapping, TAM, and ordered XRD analysis. Here we see that the FTIR of A is for cellulose, and this B is for our ionic liquid IMD-Si HSO4, and C is for our catalyst, and D for our recovered recycled catalyst. The result of characterization confirmed the successful formation of desired catalytic system. XRD analysis of sample showed peak around 2 theta degree is equals to 16.7, 22.3, and 34.5. And this XRD was similar to cellulose, showing peaks at same angle and same plane in cellulose. There is no extra peak was found for ionic liquid, as it is a very small amount and was tightly wrapped around the cellulose. Hence, in XRD pattern, the peaks for cellulose were prominent. And the SAM analysis confirms that cellulose is sheet-like structure, and ionic liquid was present on the surface of cellulose. And TAM analysis also shows that cellulose is sheet-like structure, and ionic liquid is fused on the surface of cellulose. EDX mapping was done to investigate the elements in our catalyst. There are several elements like carbon, nitrogen, oxygen, silicon, and sulfur. All are there in our EDX mapping. So we can confirm the elements by EDX mapping, and distribution of each element was confirmed by EDX mapping analysis. TG analysis, it was observed that this is for cellulose and this is for final catalyst, and it was observed that the final catalyst TGA found that the final catalyst is more stable than the cellulose. It is due to ionic liquid it increases the stability of our catalyst as it contains SiO-Si bonds. Conclusion. In summary, we have synthesized a novel heterogeneous catalyst, IMD-Si HSO4 at cellulose, for selective esterification of glycerol. We successfully synthesized triacetin in high yield under microwave irradiation under 8 minutes of time span. The present methodology offers several advantages, included sustainable reaction condition, high product yield, greater selectivity and recyclability. Thank you.
Okay, please go
And
ahead.
here is the okay, sir. Here is the contents, introduction, proposed work, methodology, result and discussion, summary and outlook, and references. And here is the introduction part. What are the supercapacitor? A supercapacitor, also called an ultra supercapacitor, is a high capacity capacitor with capacitance value much greater than other capacitor. Instead of battery, supercapacitor, and electric supercapacitor, we are using supercapacitor because supercapacitor are having high power density and low energy density as compared to the battery. But in general, we need to have both together. Both are good. And the second is supercapacitor, which provides both dedicated power density as good. In supercapacitor performance, we have high specific capacity, electrical conductivity, superior circuit stability, and mechanical robustness, fabrication scalability. And we are using supercapacitor in various applications such as flashlight, wind turbines, vehicles, computers, and other applications. On the charge storage mechanism, supercapacitors are divided into three types: electrochemical double layer supercapacitor, pseudocapacitor, hybrid capacitor. Here is the construction of supercapacitor. In construction, we are used two current collector. They are made up of aluminium, and two electrodes. Those are made up of activated carbon, and in between we used electrolyte and a separator. And here is the working of the supercapacitor. In EDLC supercapacitor, there is a formation of electric double layer. Therefore, these are called electric double layer supercapacitor. In EDLC supercapacitor, we use carbon-based materials as the electrodes. And in EDLC supercapacitor, there is a non-periodic process, which means there is no chemical reaction takes place between the electrolyte and the electrode. In other case, that is pseudocapacitor, we use polymer, that is conductive polymer based materials, and metal oxide as electrode materials. In pseudocapacitor, there is a periodic process, that is there is a chemical reaction between the electrode and the electrolyte. And here is why we are using metal oxide, because metal oxides are having high surface area, multiple tension generation, wider optical band gap, IV porosity, and charge transformation and transportation, visible light absorption, good conductivity, numerous active sites. And we are used to metal oxide in various applications such as catalysis, biomedical, agriculture, medicine, energy storage, environmental and energy, optical and electronic, information technology, and many more. And why we are using MnO2? Because we are having many sulfides, oxides, such as ruthenium, ferric, and cobalt, and nickel hydroxide, copper hydroxide, and molybdenum sulfide. Instead of these, we are using MnO2 because MnO2 is an ideal electrode material. MnO2 itself is a cheap, environmentally compatible, and has high theoretical capacitance value, that is about 1300 Faraday per gram, and it is toxicity is very low level. And here is the aims and objectivity of the proposed work. Our main aim is to synthesize the MnO2 nanostructure by one-pot hydrothermal method, and the material was characterized using the several methods, include XRD, FTR, FESM, and UV visible spectroscopy for the conformation. And the electrochemical performance of the material can be studied using the cyclic voltammetry, galvanostatic charge discharge, and the electrochemical impedance spectroscopy. And the novelty in this work is we reported a MnO2 nanostructure by one-pot hydrothermal method and prepared MnO2 nanostructure electrode exhibit admirable cyclic stability with 84.03% of capacitor retention even after 3000 cycles, significantly higher than those of the other MnO2 based electrode material for supercapacitor, which are previously reported as per literature review. And here is the methodology. We are used manganese 2 sulfate tetrahydrate and potassium permanganate and deionized water throughout the experiment. Here is the preparation of MnO2 nanostructure. First, we have to taken 0.7 gram of KMnO4 and 1.1 gram of MnOSO4 H2O in the 50 ml of deionized water, and these two solutions are vigorously stirred for 1 hour. Then they are transferred into the stainless steel autoclave about 12 hours at 180 degrees Celsius. After cooling to the room temperature, the product was washed several times with water and ethanol and dried for 12 hours about 60 degrees Celsius temperature. Then the final product was MnO2 nanostructure. And we are used different characterization techniques as I told before. And here is the fabrication of supercapacitor. And come to result and discussion. Figure 1 shows, in figure 1, A shows the XRD, B shows the FTIR, C shows the UV visible spectra. In XRD spectra, the diffraction peak at 2 theta is equal to 26.17 degrees 1 degree and 33.95 degree, 37.35 degree, 39.59 degree, 41.05 degree, 51.36 degree, 55.19 degree, 61.88 degree, 65.08 degree, and 71.21 degree, corresponding to HKL plates such as 310, 102, 211, 420, 301, 411, 600, 521, 002, and 430 crystal planes. These sharp peak implies that the MnO2 nanostructures are crystalline in nature. In figure 1, the B shows the FTIR spectra. The major peaks at 520 and 730 centimeter inverse attributed to the metal oxygen bending vibration confirms the MnO2 nanostructure. And here is the UV visible spectra. The maximum absorption peak at 420 nanometer and is obvious sign of the formation of the MnO2 nanostructure. And here is the FESM results. And A and B are the FESM results of the MnO2 nanostructure. It shows mixed morphology of nano rods, nano crystals like polygon and other crystals. And here is the EDX spectra. It is composed of the Mn, that is manganese, carbon, and oxygen. Here is the weight percentage. And the figure 3 shows the.
Yes, Sapna, can you finish within 1 minute?
Yeah, sir. Figure 3 shows the CV and GCD and ES cyclic stability of the MnO2 nanostructure. We can see in CV structure there is a rectangular shape, and that is because of that shows the ideal behavior of the supercapacitor. And here the GCD, for the various current density, we obtain a nearly symmetrical triangular shapes that also indicates the ideal behavior of the supercapacitor. In EIS spectra, in high frequency, there is a semicircle, and in low range frequency, there is a straight line that also represents ideal behavior of the supercapacitor. In a cyclic stability, there is a 84.3% of the cyclic stability after 3000 cycle. And here is the summary and outlook. We synthesize the MnO2 nanostructure by simple one-step hydrothermal method, and the formation of MnO2 nanostructure were confirmed by XRD, FTIR, UV visible, and galvanostatic charging of MnO2 nanostructure electrode exhibit a high specific capacitance of 197 farad per gram at a current density of 1 ampere per gram.
Sapna,
It consumes at
Sapna,
yes, sir.
can you give the conclusion part, please?
Yes, sir. This is the conclusion, sir. The synthesized MnO2 material exhibit a 84.03 capacity retention even after 3000 cycle. It confirms that MnO2 nanostructure material is a desirable prominent candidate to supercapacitor and as well other energy storage like battery, sensor, and other applications in future. And the acknowledgement.
Okay.